going to be and the greater the force. So why don't I make rockets bigger and bigger and bigger and put more and more fuel and burn more fuel per time? Why don't I do that? Because the rockets also get too heavy. So you have to find the right balance between the mass of the rocket and the force of the engines pushing the gas out of the bottom of the rocket. Okay. So
20 seconds.
here we're going to look at a little launch of a Saturn rocket. And I want you to look when it starts moving up,
12,
the change
11,
in velocity.
9,
I want you to watch that number.
Sequence starts. 6,
And you'll see how the velocity
4,
continues to
3,
increase
2, 1,
more rapidly
0.
as it starts moving up.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
We got a roll program. Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on proper heading. Plus 30 seconds.
So during this 31 seconds that we watched this thing, the velocity continued to increase, but it continued to increase actually more rapidly each second than it did when it first started, because the rocket had a lot of mass when it started. As it burned some of that fuel up, the mass got less, and so actually the acceleration continued to increase, and the velocity therefore increased more rapidly. Okay. So now let's look at all three laws. And basically what's happening is all three laws are working together all at the same time. It's not that one law works first and then the next law works. They all three operate together. Okay, the first law says the thrust force is greater than gravity. We have unbalanced net forces, and the rocket therefore moves in the direction of those unbalanced forces. The second law tells us how fast that rocket accelerates, and it moves directly proportional to the thrust of the engines and inversely proportional to what the rocket weighs. As the rocket continues to get lighter, it actually moves faster. And the third law tells us that the direction that it moves in is exactly opposite to the direction that the gases flow out the engine, because every action has an equal and opposite reaction. So this is how the three laws all work together. Okay. Now there are a couple of other forces on a rocket. We've already talked about weight, which is the force of gravity, and thrust, which is the force produced by the engines. The two other forces are drag, which is the friction on the fins and the body of the rocket, and then lift, which is air flowing over the rocket, moving it in the opposite direction. Okay, so the rocket is pulled towards the Earth by gravity, and the way weight acts on a rocket, it acts on what we call the center of gravity on the rocket. And we can show you that. If we take this rocket, and this is going to be similar to what you're going to build. If we take this rocket, there is some place where this rocket balances. And I can figure that out by putting it on this little test rack we have here. Okay, and if I move this little balance point, I'm going to find that this rocket is going to tip at exactly there. So right here, this point right here is the center of gravity of the rocket. This is where half the weight of the rocket's in front and half the weight of the rocket's in the back. And so when this rocket is moving up, gravity is going to be pulling down right in the middle of this rocket. Okay? That's the center of gravity of the rocket. And what you do to make rockets fly straight is, as the rocket tilts in one direction, you have to straighten it up again. And you can do that by swiveling the engines at the bottom of the rocket, or by swiveling the fins at the bottom of the rocket. So here we see a rocket there, the fins actually turn. We actually don't use that much. Do we use that in some rockets?
Yeah, a lot of rockets that stay in the atmosphere basically use fins because it's most efficient.
Okay, but most rockets today work what's called, we put the engine on what's called a gimbal mount. We let the engine swivel, and by swiveling the engine, the thrust therefore changes direction, and we can straighten out the rocket. So that would sort of look like this. As the rocket is flying, we have this guidance system in the front of the rocket that is keeping track of what direction it's traveling, and we send signals down to the gimbal mount, and we move the rocket engine so that the rocket flies in a straight direction. Okay. The other forces acting on the rocket are what's called the aerodynamic forces. And this all revolves around what's called the center of pressure of the rocket. And this is really important for your rocket. Okay? So if you looked at all of the air flowing over this rocket, the air forces on this rocket are going to determine which way it's pushed. And the way you compute that, if you figured out the surface area of this entire rocket and the fins, you could figure out where the center point is based on the total surface area of this rocket. And we can demonstrate this for you by using a weather vane. So here's a simple weather vane, and if I turn on the weather, notice that this weather vane always turns so that there's little arrows in the back, correct? If I start it like this and I let it go, it always turns back towards this direction. And why is that? Because the air is moving across and it's hitting this part. It's not hitting any of this. What happens when I put fins in the back that are bigger than the arrowhead? Which way is this arrow going to turn now when I let it go?
The other way.
What?
The other way.
The other way. It's going to turn like that. Okay? And it's always going to... Whoops.
He broke it.
I broke it. I broke it.
What's important about this is it creates the stability. You have to have the CG of the rocket in front of the center of pressure.
So see this rocket? This rocket always going to turn this way so that the larger surface area is always going to be in the back. So if I think about my rocket here, what would happen if I didn't have these fins on here? This rocket will tumble. It will actually turn over. But with the fins down here, this is always going to be in the back part, and this is always going to be in the front part as it's moving up. The air is going to straighten the rocket out so that it's always going to fly in this direction. Just like this weather vane, when I let this go, it's always going to turn back like that. Okay? So you must keep the center of pressure always below the center of gravity.
And this is important when you start using the simulator because this is the criteria that's used to say your rocket's okay or it's not. You'll see that tomorrow afternoon.
Okay.
Tomorrow.
So this is where the center of gravity will be, but that's where the center of pressure is. And if I keep the center of pressure below the center of gravity, this rocket will fly true and straight. And that's going to be really important. Okay, I think we're actually going to break, and we're going to pick up the lecture first thing in the morning and talk about rocket failures and the simulator.